as a first keynote speaker, invited speaker. You are welcome. So, there's a lot of lasers. You make your
Yeah, so thank you. Thank you very much. It's a real pleasure to be here another time to try to tell you about what is our one of our recent research in the field of artificial intelligence. So here I want to show you, and I want to share with you our vision of the field. So before, let me thank the people in my lab who collaborated in this work. So here are the people in the lab, and in my lab that is called Nanoscience Laboratory. So we are working essentially on two different topics. The first one is the development of advanced nanomaterials, and the second one is silicon photonics. And in silicon photonics, what we are doing, we are working on three different topics: so quantum photonics, which I addressed yesterday, and then non-Hermitian photonics and neuromorphic photonics. So if you are interested, so please feel free to go to the webpage of the lab, and so where you can find all our activity, and specifically you can find the highlights of last year research activity, as well as a paper I wrote 1 year ago, which essentially summarized my research activity in these last 30 years in silicon photonics. So today I would like to talk about neuromorphic silicon photonics, and I want to share with you our road to try to implement this vision, where we try to merge together to make an hybrid artificial network, where we put a biological, so a living neuronal culture on top of a photonic integrated circuit. And so what we try to do is that we try to make those two different platforms to compute together, or if you start from the biological side, to think together. And the vision we have is to use this platform for a kind of application I will tell you in a while. So let me start with the photonic platform that has been implemented by using silicon photonics. And here essentially the idea is simple. So we have, as we already saw, an optical table full of different optical components, laser lenses, and so on and so forth. And what we want to do is that to squeeze everything in a very tiny and small integrated photonic circuit. And the reason is simple. From a scientific point of view, so if we can do that, so then we can have more efficient devices, because we have much more stable devices. We have lower noise from the environment, we have lower losses. From an application point of view, so the possibility to integrate everything on a silicon platform allows us to make cheap devices with a small dimension, and then also you can fabricate volume in large numbers. So here we try to implement a different paradigm in photonics, that is neuromorphic photonics. So neuromorphic means that we are trying to get inspiration by how the brain is working. And the reason is simple, because the brain has a very high performance in a very small form factor, as well as a very power efficient device. And just to give you an idea of what is the efficiency of the human brain, so this is nothing else than the evolution of artificial intelligence in terms of the number of neurons that are used in this artificial intelligence software. And what you see is that during the years, so nowadays we are using artificial models that implement trillions, hundreds of trillions of different neurons within a single model. Just to give you a number in terms of the power consumption of these artificial models, now, so you know that this new model of artificial intelligence that's called ChatGPT is extremely powerful. You can do a lot of stuff with that. But just to give you some idea, so the amount of energy that has been consumed just to train version 3 of ChatGPT is in the order of 1 gigawatt hours. So this means to put this number in context, let us see the human brain. And let us consider the time that we take to train a human brain, or at least to start training a human brain. So consider 20 years. And so typically a human brain is an efficient device, so it consumes something like of the order of 20 watts to think. And this is also the reason why we do not lose weight by thinking. And so you have to run or to do other activity. Anyway, so you consider 20 watt, 20 years to train the human brain, so you end up to 3.5 megawatt hour in order to train a human brain. That means that by using the same energy that has been consumed simply to train ChatGPT, so you could grow up 500 people. Yeah, and then this shows you that actually artificial intelligence is really power hungry. And then people say, so one way to avoid this energy consumption is to use photonics. And so many different photonics network, neural network, or artificial model have been implemented. And why do we want to use photonics? But you say light is fast, is power efficient, you have a large number of degree of freedom, so wavelength division multiplexing, time division multiplexing, power division multiplexing, and so on and so forth. But let us consider what does it mean that light is fast. So go back to our brain. Go back to the 20 years to take a training of a human brain. And now we compare the time that a photonic components take to switch, and we compare with the time that a neuron takes to switch. And so typically biological neurons work on a time scale of millisecond. Photonic device, they do work on a time scale of picosecond. And therefore here you have a factor of 10 to the 9th. And therefore, if we are able to make an artificial optical brain, to train the brain and to take this brain at that level, so we will take only half a second. And so this is the powerful of photonics. You have a platform where you can implement a photonic computation which outperform electronics computation in terms of speed as well as energy consumption. And I want to show you an example of the application of a very simple photonic neural network on a very relevant problem. And the only basic building blocks that you have to know in order to understand the device that I will show you is what is called a thermal phase shifters. And so here what you have is that you have a waveguide where the light is traveling. And then on top of this waveguide, you place a small wire, a metal wire. And then you let the current to flow through this small metal wire. And so the current that flows through the metal wire due to the Joule effect heat up the wire. And therefore you have a heat flow from the metal wire to the silicon core of the waveguide that induce a temperature change of the silicon core. But if you change the temperature, then you change also the refractive index of silicon. That means that now your light that is propagating in the waveguide suffer a phase shift. And therefore now you have a tool by which you can change the current here, which means that you change the phase of the light that is traveling in the waveguide. And so this is the device that we are exploiting in order to train our photonic circuit to do what we are interested that the photonic circuit does. And so this is the thermal phase shifter. Let me go back to the neurons now. So you know how a neurons work. So typically the neurons get the signal from nearby neurons through a synaptic connection, accumulate all these signal via the dendrites in the soma, in the body of the neurons, and depending on the intensity of the input signal, the neuron can fire a signal out of itself. And so this is the biological neuron. And so then a few years ago, it was proposed a mathematical model of this biological neuron, that is the perceptron, where you have an input signal. And then what you do is that you sum at the input of a nonlinear node, the input signal, and what you do in order to train your neuron to do what you are interested that the neuron does is simply to change the weight of the input signal by which you do a weighted sum of the input, and then you nonlinearly transfer the sum into the output. And now you have a desired output, and you control the desired output depending on the input by simply changing the weight in the sum. So a very simple device that is called a perceptron. And now what we do is that we implement in optics a perceptron. So we are making an optical neuron. And in order to do the optical neuron, so what we did, we need a device that allows us to make the weighted sum. And this is very simple. It's an optical coupler. So you take two waveguides, you approach those two waveguides together so that you have a coupling between the two waveguides. And so the light from one waveguide coherently sum with the light from the other waveguide. And so in the output waveguide here, you have the weighted sum of the two input waveguides. And then you have a photodetector that performs the nonlinear activation function that you are interested in. And now we have integrated everything in a very small, simple device that is this, what we call a complex perceptron. So we have a fiber, then we have a grating, and in this way, we input the light into our photonic circuit. Then we have a splitter that divides the very same signal along those four different waveguides. And then we insert delay lines along all those four waveguides. And the idea of having the delay light is that in this way, we have a delayed version of the input at this level here. A delayed version means that when the light is going through, at a certain time, we have that along those four different waveguides is traveling the signal in the present, as well as delayed version, so the signal in the past, in a longer past, in an even longer past. And so now we can interact the signal in the present with the signal in the past. Then we do add our phase shifters, and therefore we are now adding a given phase shift to the different signal here. And therefore what we end up with at the end is that in this point here, we have a sum, a coherent sum, means an interference between all those different signals from all those different waveguides. And we do control the extent of the interference, meaning that we are doing a weighted sum of the signal in the present with the signal in the past. And then we have the nonlinear function performed by the detector. And therefore, what we have now, we have the possibility to influence the value of the signal after the perceptron by controlling the current that is flowing into those four different phase shifters. And this is the complex perceptron. This is the photonic equivalent of a neuron. So this is the actual device. So just to give you the size of the complex perceptron, so a few millimeters square, so very tiny. Here you have all the wiring that is needed to inject the current. And then you apply this complex perceptron to a very significant telecom problem. So you know that if you have a fiber, a very long fiber, you know that these fibers show chromatic dispersion, meaning that the refractive index depends on the wavelength. Now, if you have an input signal that you send to a fiber, due to the chromatic dispersion, you have that the pulse suffer a time broadening. And so instead of having your very narrow pulses, you get a broadening of the pulse. But since you have a train of pulses in the input, so then you have a broadening of each one of these pulses, which makes intersymbol interference, and then you lose the information. Meaning that if you are looking here, you don't know whether this is a 0, or if you are looking there, you don't know whether this is 1. And this is chromatic dispersion that severely limits the speed at which you can send your data into an optical fiber or the distance, the length of the fiber. And now what we want to do is that we want to use our very simple device in order to recover the signal after the chromatic dispersion effects. So here the idea is very simple. So we have our train of pulses, and then we have our signal after propagation into the 100 kilometer, in this case, 100 kilometer optical fiber. You see that we have lost the information whether you have a 1 or a 0. So that if you look at the histogram of the transmission, so you see that this is the histogram of the level after being propagating through the fiber. And here you have a confusion zone. So in this zone here, you don't know whether this is a 1 or a 0. So that means that you are sending an information to your friend, and then the friend cannot understand you because you have the mixing between the 0 and the 1. And so what we want to do is that we want to train our network to separate these two histograms in such a way that we know that those are 1s and we know that those are 0s. So it looks quite important function. Is it the network working? So here is the results. So this is the input. So these are the signal, the histogram of the signal level after 100 kilometer propagation. And you see that you have lost the separation between the 0 and the 1. And here is what the network is doing. So you recover the two histograms, the separation between the two. And therefore, by using the neural network, so you are able to recover the starting information. Another example, so this is already Yanis has shown this kind of A diagram that is in telecom are very well used. And the reason is because now, if you look at the eye diagram, you see that in this case, as you have a codification of the signal in 4 different levels. At input, you have 1 level, the 2nd level, the 3rd level, and the 4th levels. And those levels are very well separated. Well, that means that you can really distinguish the 1 from the 2, from the 3, from the 0. And look at the speed here. So it's 20 gigabit per second, and the length, 100 kilometer. And then here you have the output, the very same eye diagram after propagation in the fiber. You have completely lost the difference between the different levels. And so this means that this is useless signal, okay? And then now we apply our neural network, and what you get again the eye opening, meaning that now you are able to distinguish between the 3, the 2, the 1, and the 0. And this is done by using photonics. You do not consume power, and you perform this kind of chromatic dispersion mitigation online, and with that very simple devices. So this is the one example of photonic integrated circuit that allows you to make an artificial neural network. But then we try also to do the biological network. So biological network, what does we mean is the fact that now we cultivate neurons. And what we want to do is that we want to use light in order to influence the neuronal activity. And in order to do that, what we do is that we use a technique that is called optogenetics, by which we do insert on the membrane of the neurons a light-sensitive protein. And then by using light, we can open the ionic channel through the membrane and depress the neuron activity simply by using light. Now we cultivate our neurons, and then we spot a light pattern on top of the neurons. Here is an example. So those are all the neurons. Those are the light spots that we are shining. And what you see is that now, depending on where we excite the neurons, we are able to activate a specific circuit inside our neuronal culture. And therefore, now we are able to, on one side, influence the activity of the biological culture by using light, And then on the other side, we are able to compute by using a photonic circuit. And now the vision is to merge the two platforms together, so making an artificial hybrid biological network. And so here is the device that we have developed. So here is the photonic circuit. Here you have a fiber array just to couple the light into the photonic circuits. Here you have a series of fiber. Then what you do, you place everything under a microscope in order to be able to see the neurons that you have. So those are all the fibers. Here you have the photonic circuit in a Petri dish. Everything is compact. And then you plate the neurons on top of your photonic chip. So this is a optical microscope images. You see this stripe there are the the waveguides, and then the small spot here are the neurons. You look whether the neurons are alive, so they are alive, so they are well behaving. And then now what you do is that you shine your light into your photonic circuit, and then you force the light to output from the circuit in very specific points, like in this case. So we have a matrices of points. And then you put your neurons on top of those points. You tag the calcium that is showing the activity of the neurons. And here is the result. So the small blue points here are the light that is exiting from the photonic circuit, and the red point there show the fact that the neurons are active. And what you see is the fact that this is a blow up of the previous image. You see that by using light, so you're able to influence and activate the activity of the neurons. So then now we have this hybrid artificial network. What for? So here the vision, so this is not what we are doing now because we are still working in vitro, but the vision is to use this kind of hybrid artificial intelligence, circuit in order to support malfunctioning brain sectors. And specifically what we are targeting are two different applications, which I can tell you more maybe during the discussion. And if you are interested, so this is a link of videos where we are trying to explain what we are aiming to do, is that the two different application is in the epilepsy field and in amnesia field. And by saying that, I think here that I need to stop. I acknowledge the different funds and you for your attention. Thank you.
Thank you, Lorenzo. Great story. We have not so much time for questions, but single, very precise one, if somebody wants. No, okay. Thank you very much.